Thank you, everybody. I appreciate very much appreciate the hospitality that you've all given me today and tomorrow as well. I want to especially thank Kevin and Ed and the kind folks of the Department of Physics and Astronomy for inviting me. It's a proud place to be. I really am impressed with the University of Nebraska. I've never been in the state of Nebraska before, and this is the best place to start a tour. And I very much appreciate the opportunity to talk to you tonight about one of my pet interests, rocks falling from the sky. And if you didn't already get one, there is a quiz for everybody here on the chair by the door that we came in, and Dr. Lee will be handing out to those of you that missed it on your way in. We put it there so you'd stumble over it. But as I'm finding in my own classes, people will make a habit of walking around papers by the door rather than picking them up. We have a high-tech solution to our audio-visual problem. Dr. Schmidt will be clicking for us tonight. I will give him a round of applause for his technical ability. If we could try him out, first click. I'll give you a little bit of background on why I'm here. One of the main reasons that I'm here is because the American Astronomical Society takes it seriously that one of its prime responsibilities is helping the public understand what astronomers do. We don't cast horoscopes. We don't do stargazing in the sense that an amateur might do. We do a lot of cool things, but it's most people's impression that astronomers stand around looking through the eyepiece of telescopes. Yeah, occasionally we'll do that. But I'd like to give you a little bit of background on why the American Astronomical Society has this sense of responsibility to the public. You pay for much of what we do. You pay for the research grants that we get. You pay the tuition that the universities charge you to take the classes that we teach. You have every right to know what astronomy and astronomers do. And aside from that, it's really cool stuff, and we're happy and proud to tell you about it. Now, Harlow Shapley, the gentleman in the upper left-hand corner here, was someone who felt even more strongly than I do about the subject of telling the public what's going on in our discipline. You all probably know or know who Carl Sagan was. Harlow Shapley was, in a very real sense, the Carl Sagan for the science of astronomy for the better part of 40 or 50 years, through most of the 20th century, right up until the day he died in 1972. He was probably among the top 5 scientists in the world in terms of public recognition and influence on science policy and science education. His claim to fame, though, started in around the 1920s when, in his PhD dissertation, actually it was the 19-teens, in his PhD dissertation, where he got the brilliant idea to use a technique very similar to the technique that Dr. Schmidt is now doing in a much more advanced way, studying stars whose energy output vary, who actually pulsate in size. And early in the 1900s, it was discovered that certain variable stars called Cepheids, the pole star, the North Pole star, Polaris, is one such example, pulsate. They change in brightness. And the surprising thing about them is, as the first distances to Cepheid variable stars began to be calculated, it was rapidly realized by Henrietta Leavitt at Harvard University that the longer the period between the brightenings, the brighter the star was on average, and the easier, and of course when you know how bright something actually is, and you measure how far away it is, you get distances to whatever system of stars that a Cepheid variable is in. And he got the brilliant idea that he could investigate these mysterious globular clusters that you see peppering the whole sky in various directions, and get distances to them if he could find at least one Cepheid variable in each one. And he did that. And he got distances and the positions in the skies, and he plotted them out in a 3-dimensional plot. And lo and behold, he put the sun right here, say at the 0 point of a map, and he plotted all the positions of the globular clusters that he could find, each one of which has 100,000 or more stars in them. So they're big things. But if there's just one Cepheid, that's enough to get the distance through this period luminosity relation. he found that, lo and behold, these systems of globules of hundreds of thousands of stars each were all over on this half of the sky except for a smattering. That the southern part of the sky had most of the globular clusters. And that the distance that you'd have to, if you make the balance point between all of these point sources, the center is about right there, if you assume that all these are in orbit about some place that you can't see. He concluded that, wow, that must be the center of our galaxy. And he figured that it must be something like from the sun's distance in the solar neighborhood, where you see a few stars clustered around here within a few light years of the sun, must be on the order of 10,000 parsecs, something like 30,000 light years away in the direction of the system of constellations called Scorpius and Sagittarius. He did for our galaxy what Copernicus did for our solar system. He showed that our galaxy existed, which was in dispute at that time. We didn't know about other galaxies until the middle of the 20th century. And he showed that we're not at the center, we're out in the boonies. Just like we're not at the center of the solar system. Next picture. And our galaxy probably looks like that picture on the lower right, by the way, if we could get out of it and look back at it. Now go back. That, for some reason, that hit a website. You were on a picture. Just advance. Don't click on the picture. You should be able to just close that. It won't go up there. Yeah. There we go. He was the most outspoken advocate of science of his generation. He was on the cover of Time magazine a number of times. This is a picture of him in his younger days. He wrote a number of books, many of which I've read. In fact, there's 3 of them right there that chronicle his days of discovering the center of the galaxy. He was also a key player in the establishment of federal funding for science, the establishment of the National Science Foundation after World War II, and the United Nations Educational, Scientific, and Cultural Organization, UNESCO, which still exists. And probably equally important, he was one of the foremost scientists who spent a lot of his time debunking what euphemistically can be called para or pseudoscience. Wild, wacky claims that have no basis in science, such as Immanuel Velikovsky's claim that Venus was a comet that veered so close to the Earth and a few thousand years ago that it created all kinds of cataclysms that gave rise to civilization mythologies that he cited. He spent a lot of time debunking things that the public were being deceived about. And his responsibility to skeptical and inquiring and scientific thought for the public was one of his major concerns. So it is to his credit that we're here tonight. And he established in his will an endowment that funds to this day at least part of the expenses of the Shapley program. Next picture, please. Yeah. Well, speaking of pseudoscience and false science, I'm sure you've all seen National Enquirer magazines and movies like Deep Impact and Armageddon. If you are any kind of a science geek, you know that those movies and those articles are just plain nonsense for the most part. Trying to stop a comet that's going to hit, or asteroid that's going to hit the Earth with a space shuttle equipped with a nuclear warhead is just ludicrous from several angles of scientific approach. And of course, let's not even talk about making up the idea that astronomers are hiding the evidence that there's a big killer asteroid on the way. That is not going to happen. You're going to know the second the astronomical community knows whether there's a threat, and I'll tell you how during this talk. So anyway, keep your eyes and ears open and apply a little bit of critical thinking, and with the information that I give you tonight, you'll be able to spot the things that are questionable from the things that are worth looking into in this subject. I hope. Next picture, please. Well, let's start with the fact that impacts do happen. We've seen them. We suspected for many generations. You look at the craters on the moon. There's a crater right here in Nebraska. Did you know that? Haven't been out to it, but they're one of the biggest craters around in the United States is here in Nebraska. In 1994, we saw the fragments of comet Shoemaker-Levy break up in a close passage around Jupiter, and on the return on that orbit, it actually hit Jupiter. We have seen an impact occur. And some of you probably saw those pictures. If you were grown up enough to be paying attention to the astronomical news, you saw these pictures from this space telescope showing the atmospheric impacts of the shards from Comet Shoemaker-Levy. The Earth would fit nicely inside one of those dark spots that lasted for several weeks. It's a good thing that we weren't hit, because it would have global ramifications. Not the destruction of the entire world, but at least global ramifications on civilization. So it does happen. We've seen it. Next picture. And the reason for taking this seriously is because this process is ongoing. It's what built the planets. It's why we're here. It's not a bad thing unless you're at ground zero. It's why planets exist. It's the end product of planet building. So this is probably what the Earth looked much like in the early years of the solar system. In the first few 100 million years of the solar system, there was probably little chance that there was a firm crust, because impacts were taking place about once every 100 years that would vaporize large sections and leave the crust of the Earth unstable. So it wasn't a pleasant place for the first billion years or so of the solar system. Next picture. You might have to just do a click ahead to get around the video on that one. Do the arrow, the cursor, the little cursor thing. There we go. Now, all of you have seen shooting stars, right? A misnomer on several fronts. First of all, they're not shooting. Nobody shot them. And second of all, they're not stars. But these meteors, as they're called, are pieces of the solar system that fall to the Earth. And our question as scientists is, where do they come from? We solved that problem roughly 150 years ago. I'll tell you in a minute. A little bit of nomenclature. Meteors are the flash that you see in the sky. In principle, when they're out in space, these fragments are called meteoroids. And in principle, if you find them on the Earth, and I brought a couple of samples here in you can look at after the talk if you want to, they're called meteorites. So just a little bit of nomenclature. Meteorites is what most people have seen physical samples of. Meteors are what you see in the sky as flashes. Where do these come from? How do we know where they come from? Next picture. Well, one theory would be, since we see comets come by, that comets are clearly losing material, and Comet Hale-Bopp, which came by about 10 years ago, was one of the brightest comets of the century. It would have been visible in broad daylight had it come anywhere close to the Earth, but it was about as far from us when it was brightest as the Earth is from the Sun, and even at that it was still one of the brightest comets we've ever seen. Had it passed as close to us as Comet Halley did, you would have been able to see the tail spread across the entire sky, and it would have been visible in broad daylight for a few weeks. It was a whopper of a comet. So clearly comets are losing debris. We see the gas coming off and being ionized. We see the dust coming off and reflecting sunlight. Are debris from comets, where flashes of light in the sky called meteors come from. One hypothesis, one educated guess. Let's prove it one way or another. Next picture. That's a picture I took from my backyard, by the way, of Comet Hale-Bopp in the previous one. Well, as it turns out, if you plot the orbits of comets, and you plot the spot in the sky that meteors look like they're radiating from, and how it moves in the sky from night to night during a meteor shower, you can figure out the orbit of the debris that's burning up in the atmosphere. And we find that in most cases, the annual meteor showers that we experience correlate rather nicely with the orbits of comets, known comets. And so pretty much to 100% confidence, although in science nothing's 100% confident, we can confidently state that most of the flashes of light you see in the sky during a typical night out or during a meteor shower are from comets. Debris that comets in their previous passages have have spewed throughout the orbit that they exist. And every time the Earth passes through one of them, it's like in Florida when you're driving I-95 during love bug season, you get pasted, your windshield gets pasted with love bugs. Well, the Earth's windshield gets pasted with love bugs from space on an annual basis as we pass through those streams of debris. The typical object, you can work the physics out, is that causes a flash visible to the naked eye is smaller than a grain of sand. But it's moving on the order of 20 to 30 kilometers per second. And at that rate, it burns up almost instantly in the upper atmosphere of the Earth at about an altitude of 60 kilometers or 40 miles or so. And that's enough to cause most of the flashes. If you go out tonight and you just lay flat on your back on a chaise lounge or a nice warm sleeping bag, it is a little cold out there, you should see a meteor something like once every 10 or 15 minutes, and a really bright one about once or twice a night. That's the normal rate of infall of naked eye meteors. But during a meteor shower, as the one that's called the Leonids, every 33 years, 10,000 or more per hour can be sighted. It can literally look like the end of the world in some cases. And this is a picture taken of the Leonids several years ago when they were at maximum. That's an exposure of something like 20 minutes, so that many meteors in 20 minutes. So, tentatively, we'll identify the typical shooting star that the average person sees with debris left over from comets. Not to worry, it never gets to the ground. Next picture. That's not where the interesting and thought-provoking material... Oh, I forgot. I put in a list of this year's meteor showers that you can look up anytime you want in Sky and Telescope or Astronomy Magazine, or just do a Google on meteor showers. You'll find a list anytime you want. So we don't need to dwell on that too long. But there's about a dozen per year worth looking out for. Next picture. Well, geologists and astronomers who are interested in impacts have scaled the world, some places better than others, and found something like 200 impact sites around the world. And in the United States, I'm guessing that's the one right about there that's in Nebraska. There are about 200, and in this map, look how many are in the United States compared to the rest of the world. Is there an explanation for that? The United States having been hit more often than everywhere else? No, not really. It's just that this country's been looked at more for meteorite hits than others. And how many people out here in the far reaches of the Asian deserts do you think are scouting around looking for meteorite impacts? Also, remember that the Earth is a very active planet. It's geologically active. It covers up the impacts that have occurred. Erosion covers them up. Tectonic activity and volcanism covers them up. Wind erosion covers them up. Superhighway construction covers them up without even knowing it sometimes. So the Earth is very actively getting rid of craters. We should look like the moon if they weren't being erased. So this 200 or so known astroblems, as they're called, is just the tip of the iceberg. They're the biggest and newest ones that Mother Nature hasn't been able to erase yet. How many of you have been out to northern Arizona to Meteor Crater? In a room this size, a few of you probably have. I strongly recommend that if you ever go to Grand Canyon, you make a side trip. You can do it all in a day. Go over to Meteor Crater, Arizona, and visit one of the newest craters on the face of the Earth. It's a measly 50,000 years old, and it looks, for all intents and purposes, like a big round gravel pit. Next picture. I've got a picture of it here later on. Well, I'm not going to climb down and point to it, but there's a sample of a type of meteorite that has fallen to the Earth down here that you can look at. There are several classes of meteorites that have typically been discovered as falls. That's what they're called when they've actually hit the Earth. By far and away, the most common are called stony, because they just look like stones. They're hard to tell the difference between stones that just naturally occur on the Earth and stony class meteorites. But the differences are significant if you know what you're looking for. And then an interesting subclass are iron meteorites, which are iron, nickel, and cobalt and then the rarer combinations of rocks mixed in with iron. There's a sample of the iron type down here that you can look at after class. But if you cut it open and take vinegar or some other mild acid and just wipe it across that open, flat face, you get these little crisscross patterns, which prove that it's from outer space, because iron and nickel will form those Widmanstätten patterns, as they're called, only if they have been allowed to cool from the molten state very slowly. And that doesn't happen on the Earth's surface very much. And also, you notice that no oxidation has occurred. Well, what iron on the face of this planet doesn't get oxidized? So clearly, if it's in the vacuum of space, in the absence of water and air, oxidation is going to be rare. So where do these come from? Are they pieces of comets, or is there some other place for them? Next picture. Is there some other source of them? Well, we know they hit other objects than the Earth. In fact, this is something you could do right now. The International Occultation Timing Association, IOTA, and a lot of amateurs are now, every time there's a meteor shower scheduled, they'll go out and start videotaping the moon, because the moon has no atmosphere. Meteors aren't going to burn up in the moon's atmosphere. They're going to hit the surface immediately at 20 or 30 kilometers per second, causing a bright flash. And here's one of the first photographically recorded meteorite strikes on the moon's surface, 1950-ish, if I remember right, 53 to be exact. Well, now during the meteor storms, it's not uncommon to see 2 or 3 hits. Again, these are just little tiny grain of sand type things causing a flash that's recordable on video cameras. So clearly the moon's still getting hit. That's where much of the moon's soil came from, as a matter of fact, the lunar regolith, caused by impacts. In the year 2000, the most recent major Leonid meteor shower, the impacts were videotaped by about a dozen sites. Next picture. And then another interesting aspect of meteorite study is that Antarctica is the happy hunting ground. Why? Because it's white. It's not doing anything. It is the driest place on the planet, and these ice sheets are gradually sliding downhill towards the ocean, where they fall off as ice sheets into the ocean and icebergs, and all the time gathering up like a conveyor belt anything that falls on them. So one of the things that some of the scientists that winter over at the South Pole do when the sun finally comes up above the horizon is to go out and look for black dots on the surface of the ice sheet, and you find meteorites by the dozens if you're careful enough, and that's where many, probably a good fraction of all known meteorites have been gathered on the Arctic and Antarctic ice sheets. One that's particularly noteworthy is one that was found in 1984, hence the 84, in the Allen Hills region of Antarctica. It was the first one found in that region, so its designation is ALH 84001. In 1996, a paper appeared released by NASA researchers that showed microscopic photographs of a slice of this that showed structures very similar to microfossils that biologists identify in Earth rocks as ancient bacteria fossils. And we really do know that life has been on the surface of the Earth for many years, billions of years, because of these microfossils. This is an interior slice, however, that's never been exposed to the Earth's environment. Moreover, the chemical abundances of this show very conclusively that it belonged to Mars. So this paper proposed the idea that Mars used to have microbial life, maybe still does, and here's fossils from Mars. Have you heard of that story before? Some of you have, but it's still, after 10 years, no longer in the news because it's not held in very high regard by the scientific community. It didn't stand the test of further investigation. But it's still intriguing that perhaps meteorites could have carried the seeds of life from one planet to another on occasion. Next picture. Of course, we've always thought there might be life on Mars. The lunar landers, we've had several now, and the subject for tomorrow's lecture will be, how we think life might exist elsewhere in the solar system or elsewhere in the cosmos. So without further ado, we'll move on to other aspects of impacts. But keep in mind that impacts might have had something to do with life starting on the surface of the Earth. It should go ahead and click to the next one. All right, now if 3 or more sites observe a fall, a flash in the sky, from widely separated locations, in principle, if those observations are accurate enough, or photographed, or videoed, you can calculate the orbit. The Allende meteorite in Mexico, and a dozen or so other meteorites that have been well documented in the last 20 years have had orbit determinations from the sightings, and if you work out the orbits, so far every one of the witnessed falls whose orbits have been calculated have been one or more elliptical shapes whose near side is crossing the Earth and whose far side goes out to between the orbit of Mars and Jupiter, where we call the asteroid belt to be located. And so we find that the things that you find on the surface called meteorites come from a different place, come from a different source than the flashes in the sky that you see very often. The flashes in the sky are more often debris from comets. The flashes in the sky that result in debris on the ground that you can recover, pieces, come from the asteroid belt. 2 families of sources. And why comets are a different family than asteroids we'll come back to in a moment. Next picture. But we're actually sampling the asteroid belt when we touch a piece of meteorite. Several years ago, an animation of all known asteroids was put together. These are all 20,000 or so asteroids known, whose orbits are known well enough to be computed. All of them are rotating pretty much counterclockwise as seen from the top. You see Mercury, Venus, the Earth, and Mars on just the inside track. I think it's right there. Yeah. There's Mercury, there's Venus, there's Earth, and then Mars, I keep losing it. It's right on the inside edge here. And then Jupiter's out here. So they're all between the orbit of Jupiter and Mars, at least 99% of them are. But the ones that have little orbits that are elliptical enough to reach us are the ones that we should be concerned about. They're the ones that are going to hit us, guaranteed, sometime in the future. Next picture. You'll have to probably click twice outside that picture. You may have noticed the color coding in the previous animation. It corresponds to places where the orbital period is exactly twice the period of, sorry, not twice, 1/2 the period of Jupiter, or 1/4 the period of Jupiter. In such numerical even ratios, Jupiter tugs a little bit more frequently on those kinds of orbits, and so the orbits of the asteroid belt have been cleaned up, and there are ratios of 3:1, 5:2, 7:3, 9:4, 2:1, where Jupiter has made gaps in the asteroid belt. Those objects get a little extra tug towards Jupiter, and so they get evacuated from that particular distance. So there really are rings in the asteroid belt, gaps in the asteroid belt, discovered back in the 1800s. Most of the time, at least in olden days, asteroids were discovered by little streaks across the sky in deep exposures. In an hour-long exposure, you might find that an object drifted just a few arc seconds across the sky, a tiny fraction of the size of the moon in an hour, and you could calculate its speed from the length of the little stripe. We don't look for asteroids that way much anymore because we have robotic telescopes that will do the job much more efficiently. And besides, the Earth-crossing asteroids that we should worry about have much higher velocities and would go completely across that photograph in a fraction of the exposure time and give us no information about their orbits. The biggest asteroid is worth noting. The biggest known, anyway, is Ceres. It was also the first one discovered. It's round. Not all asteroids are round, but it's big enough to make itself round. It's about 1/4 of the size of the full moon, and if you were to drop it neatly onto the Earth's surface, it would fit nicely into the Gulf of Mexico. That's the biggest one. For the most part, they're a few kilometers across, or smaller. Next picture. I like to bring this story up partly because it's a personal interest to me, because it was an expedition that I organized early on in my years as a faculty at FIT, but also because it's still, to this day, the most accurate determination of the size and shape of the largest asteroid. One of the ways we have of finding out about asteroids is by occultation, and that means a miniature eclipse. There's so many asteroids, some of them have to pass in front of background stars. Well, in the early 1980s, the asteroid series was predicted to pass in front of a star. And we computed the track as the north end of the track and the south end of the track was going to pass from east to west directly through our region of the United States. FIT is about halfway down the peninsula of Florida. Our observatory is there. And we deployed people in the Florida Keys and the Bahamas and then in Turks and Caicos in order to witness and record with photometric gear the drop in light as that asteroid passed in front of the star. And in a time exposure, the stars drift across the sky because of the Earth's rotation, but this star happened to disappear for 10 seconds because an asteroid that you couldn't even see passed in front of it, so it made a gap in the photo. And by knowing the time of the exposure, you can figure out the diameter of the asteroid that caused that gap. A little more sophisticated way, with all the groups that we deployed down into the Caribbean, every dot represents a disappearance or reappearance of the asteroid series, and then you can connect the dots and get the silhouette of the asteroid and compute its size, shape, density, and other physical characteristics from that data. And to this date, that's still the most accurate determination, less than 0.5% uncertainty with this technique. You don't even have to be able to see the object, you just have to be able to see the star that it covers up go away. Well, okay, we can't wait until every asteroid passes in front of a star. That's just cool when it happens. Next picture. And it's not going to give us information specifically about the Earth-crossing asteroids. But we do need to know about the families that are involved. Now, one thing that you can do for any asteroid is turn a telescope on it, use a spectrograph to get a spectrum, break the light into its component colors, and compare that spectrum to laboratory minerals. And if you do that, the minerals I have in mind are the meteorite samples that have already fallen to the Earth. If you do that, you confirm exactly what we said a few minutes ago, that nearly every meteorite can be identified with material from the asteroid belt, because here are the spectra in the infrared, here's the optical region and then the infrared region, of several classes of asteroids. An M-type asteroid is nearly all metal, and there's a sample of an M-class asteroid up here. One that's rich in certain elements, like olivine, is Vesta, one of the bright asteroids. And we find that there are meteorites that have the same spectra as these asteroids. And so that tells us again that what we're getting are samples of the asteroid belt. Next picture. So we're on pretty firm ground, thinking that the most things that we have to worry about come from the asteroid belt. We've been to many of the asteroids now. Almost every outer solar system mission NASA has launched in the last 20 years has been scheduled to fly by one or more asteroids. We've seen asteroids up front and personal. They're mostly shards of creation, leftover debris. If you've ever built a house, you know that the builders leave junk all over the place and covered up with sod so that you never know unless you're watching. Well, when the solar system was built, the debris left over was the material between Mars and Jupiter. Ida and Dactyl, that's a little satellite to an asteroid. We now know that some asteroids have satellites themselves. These objects are only a few kilometers across, typically. The size of this room would be a typical size of a smallish asteroid. You'd have to worry about an asteroid that big if it were going to hit the Earth. And we've actually landed on an asteroid. Eros, one of the Earth-crossing asteroids, was targeted earlier in this decade by the what was renamed the Shoemaker lander, and it was placed in orbit around the asteroid for several months, and then finally, since it wasn't made to land, it was more of a docking maneuver, landed right on the surface of the asteroid. The gravity field of an asteroid is so low you could literally run and jump off of the asteroid and go into a low orbit around it. Next picture. In fact, there's a picture of the surface after the lander touched on the surface of Eros. Looks like dirt. Well, that's what it is, but it's a very low density dirt, not packed very much because there's not much gravity. Next picture. We now know from studies of other stars and studies of our solar system that the Sun has several rings around it. Like Saturn has rings, the Sun has rings. The innermost ring is rocky material, the asteroid belt. But now we know there's a much bigger ring out beyond the orbit of Neptune. The very reason Pluto got demoted from planet status is because this ring, starting at about the orbit of Neptune, stretching out to about 3 or 4 times Pluto's orbital radius, is a ring made out of snowballs called the Kuiper Belt, after Gerard Kuiper, one of the first planetary scientists. And so, in addition to this asteroid belt that's very close in between Mars and Jupiter, out here beyond the orbit of Neptune, Pluto being the first such object discovered, are at least hundreds of thousands, if not millions, of snowballs, some of which are already known to be larger than Pluto. Are any of those eccentric enough in orbit or perturbed by close passages to one another to fall into the solar system? The answer is a tentative yes. Some comets probably do come from the Kuiper Belt around the solar system, but there's yet another regime even farther out. 100 astronomical units out is where the Kuiper Belt is. That's 100 times farther than the Earth is from the Sun, 2.5 times farther than Pluto is from the Sun. But 50,000 times farther out than the Earth's orbital size is an even larger cloud of snowballs called the Oort cloud. And we think most comets come from there. Most of the comets come from there. And this is debris left over from the solar system's formation that got blown and flung out of the solar system as the planets started accreting and gathering material and gravitationally flinging some of it out of the solar system that didn't run into it. And we now know that there must be an enormous quantity of objects out there in the Kuiper Belt. And we see these clouds around other stars now. We've begun to image them. In fact, on the cover of Science, the preeminent journal in the United States for all of the sciences, one of the cover stories was the discovery of several planets around the bright star Fomalhaut, and these planets are circling just inside a clear belt of icy debris that we can identify as that star's Kuiper Belt. So we're seeing structures outside around other stars that we now know our Sun has. Okay, we haven't talked about where the impact risk comes in. Let's get down to that. But the next picture, please. Oh, I forgot. I have a few pictures of comet nuclei now. They look at first glance a lot similar to the asteroids, except they're ice mostly rather than rock mostly. So at first glance they look like that. Go ahead. So that's Comet Halley, Comet Temple, Comet Wild, and Comet Borrelly. They've all been passed by spacecraft, so they've been imaged for the first time, and they're basically dirty snowballs. I'll tell you all about comets at some other time. Next picture. The story about impacts and the reason why we should be concerned about them began about 1980 when Walter and Luis Alvarez, a father and son team, one was a physicist, one was a geologist, but they both got interested in geology when they were, I think, on vacation near the city of Gubbio, Italy. That's me. We were in Gubbio one time on vacation too. Outside the city of Gubbio, about a 20-minute drive, is a gorge that has a very narrow, I would call it a 1.5 lane road, but it's a 2-lane road, going up the steep edge of the gorge. It's not a very big canyon. It's not like Grand Canyon or anything, but right by the side of the road is a single sign, nondescript. If you read Italian, you'll recognize it. But this is the site where, alongside the road, I took this picture, are exposed strata that the construction of that road ripped out, and so they're stripped bare. And that particular stratum, if you look very closely, has a dark lane through it. I think it's that one right there, if I remember right. It's the picture's not expanded enough to see, but here it is close up, and there's a coin about the size of a quarter put in there. So it's about that thick of brown material. And that brown material, if you analyze it, first of all, has a lot of carbon in it. Soot, if you will. But intermixed in that layer is also about 100 times more iridium, europium, and other trace metals that are called rare earth metals that you hardly ever find in the Earth's crust. That's why they're so expensive. But in meteorites, you find abundances 100 times that of the Earth's crust. And so Walter and Luis made the hypothesis that, wow, soot, that sounds like fire. Oh, iridium, that sounds like impact, debris from an impact, meteor. The date, geologically gotten from nuclear isotopic dating, is about 65,000 years ago. Their hypothesis, based upon this single find in Gubbio, Italy, was that at 65,000 years ago, a major impact occurred that deposited iridium, at least across Italy, and burned much of the vegetation that was burnable, and deposited that 1-inch layer.
65 million.
Did I say 65,000? I meant 65 million. Thank you for the correction. Sometimes my mouth gets ahead of my brain. 65 million years ago. Next picture. Well, it's highly controversial, as you can guess. And it still to this day is a very active area of geologic and paleontologic and astronomical research. But the test of time has been passed. This particular hypothesis is now generally accepted by most of the astronomical and geological community, because you know what? At every site around the world that this particular age of rock is available, hasn't been recycled by tectonic or erosion or volcanic processes, every place that age of rock is available to be studied, you find iridium in excess. And sometimes soot, but not always. And so that is the smoking gun, that it's a worldwide calamity that deposited iridium around the entire surface of the Earth. And even that wasn't enough to convince the scientific community of the hypothesis until, I forget the exact date, but it was around 1990, that petroleum explorers analyzed some samples that had been dug in the Yucatan Peninsula and found evidence of shock structures, microscopic crystals and fractured shock-based minerals that suggested that right there in the middle of the Gulf of Mexico is a buried half under the land and half under the Gulf of Mexico. Right there on the northern tip of the Yucatan Peninsula, straddling the coast, is a crater of something like 100 kilometers across that is, in fact, the exact age of 65 million years and shows the same kind of structure that you would expect for the impact that the Alvarezes found in Italy. Now, during that same time, paleontologists were coming to grips with the fact that across the last 500 million years or so, since life began to be prevalent on the surface of the Earth, there have been several extinction events. Each one of those spikes represents a change, either a drop in fossils or a rapid change in the kinds of fossils that take place from one stratum to the next. There have been at least a half a dozen major extinction events in the fossil records, suggesting that impacts occur more than once. And the one that's most recent to 65 million years old, or at least the one that's most recently documented. Now, David Raup and several others have proposed that these come at something like 26 million year intervals, and that would hypothesize some perturbing influence causing rocks to drop on us every 26 million years. That's highly controversial, but if you do a statistical analysis, you can see that there is a marginal evidence for some periodicity there, but not convincing entirely. If you're interested in that, you might look up David Raup and Google David Raup, and his book, The Nemesis Affair, is a very interesting read in scientific investigation. R-A-U-P is his last name. Next picture. So that's an interesting side question. Do extinction events come on a regular basis? Well, about 15 years ago, NASA and the funding agencies in general realized that it's in our best interest to at least assess the risk. So let us find and categorize the most dangerous NEOs, near-Earth objects, or NEAs, near-Earth asteroids, or PHAs, potentially hazardous asteroids. And there have been a half a dozen searches around the world now. 3 of them that I know of in the United States have been conducted and are still underway, and about 3 others outside. The typical search strategy involves a robotic telescope that uses electronic cameras to image a piece of the sky on an interval of something like 15 minutes, come back in another 15 minutes and image again, come back in another 15 minutes and image again. And that's too quick for asteroids. You won't see asteroids move much in 50 minutes. But one that has an Earth-crossing orbit is moving rapidly. And you will see it in 15-minute images. If it has the right velocity, it will be seen in one of these images, but not the others. And in this frame of 4 images right here, you see it in the first one, those are stars, and then you don't see it, and then you don't see it, and then in the next 3 frames that the telescope's moved over a little bit at the rate the object's expected to be moving, and you see it in one of the 3 frames, and then the telescope's moved again, and you see it in the last frame. That proves that you've got an object moving at the right rate to be an Earth-crossing asteroid. I'm walking across the stage right now, and those of you in the front row seem to be whizzing by, at least compared to those of you in the back row. An Earth-crossing asteroid is close to us. It appears to be moving in the sky faster than a distant asteroid would. So that's the search strategy. They're pacing these exposures at the rate it would take to find Earth-crossers. And literally, about 2,000 objects have been found so far. Not all of them are going to hit the Earth, but most of them are. Another strategy is to use radar, mostly the Arecibo telescope, but these are 2 other radar telescopes. The Arecibo telescope can actually image some of the Earth-crossing objects. This one, asteroid Untitled, was imaged about 10 years ago, and it was shown as it went right by us at one hellacious clip. It went by at about the distance the Moon is from the Earth. It's shown to have two rotation periods, and it might actually be a binary. It might be 2 objects that are touching one another in such a close orbit around one another they're touching. It's hard to say whether it's a dumbbell or peanut shape or it's actually 2 objects given the radar images resolution. But this particular object is potato-shaped and has 2 periods of rotation. About one axis it's got about a 5-day period, and about another axis it's got a longer period. You've seen those little carnival rides where you sit in a chair on 3 different axes and you spin in 3 different directions. This asteroid's spinning in 2 directions. That is a symptom of a chaotic, meaning collision origin. Collisions cause chaotic rotation, and that object was formed by a collision, apparently. And it will hit the Earth someday. Next slide. If you're interested in this, you can do a Google on potentially hazardous asteroids. Go straight to the Near-Earth Object Program at NASA. I just did that a couple of days ago. Here are a half a dozen or so close approaches of near-Earth objects that will occur this month. We're tracking these right now. And the distances that are listed here that are nominally listed in lunar distances. 11 times the distance to the Moon is the close approach to that one. Not to worry. Well, here's one that's 8, here's one that's 9, here's one that's 4. Well, some asteroids pass between us and the Moon. Some of these NEAs pass between us and the Moon, and you can get a list of those by going to that website. The next really known close approach is in about the year 2030, and it will be visible to the naked eye. It will be so close to us. It's not predicted to hit. Initially, it was listed as a potential hit threat, but this one will pass whizzing right by us, visible to the naked eye for a few hours. It'll go right across the sky. It'll take 2 or 3 hours to go across the sky, but it'll be visible. Next picture. So if you're interested in this, that's the website to go to keep up to date on it. Now, like the oil industry or like the election returns, if you take a good track of how the finds, how the discoveries are coming in, the rate new ones are being discovered, the rate new oil wells are bearing oil, or the rate votes are coming in from the different districts, you can predict how the rest of the sample is going to go. Now, we can never hope to find every one of these objects, but the rate that these discoveries have been collecting or discovering new near-Earth asteroids has allowed us to put together plots like this. From their reflectance and brightness, if they reflect like a rock and they have a certain brightness, we can estimate the size from how big it would have to be to have that brightness. And we can make a plot, for example, of the number of a certain size versus the diameter. So this is a plot of how many 1 kilometer sized asteroids there are. It turns out in this plot there are something like Oh, if you figure it out, about 2,000 was the original estimate. The discovery rates have tapered off a little bit in the last 3 or 4 years, so the best reliable estimate we have is more like 1,000 objects out there that are going to hit the Earth someday that are 1 kilometer in size or smaller. There's something special about that size I'll come back to in a moment. 1 kilometer is about the size of the campus. Okay? Small, but Earth calamity is a 1 kilometer size. Another thing that we can do is, based upon the nature of these orbits, is to make a plot of the risk or the frequency. How often an object of a given size will hit the Earth based upon the orbits that have been discovered, and what the energy yield will be for an object. It's really easy to do that. If you've had intro physics, you know that kinetic energy is 1/2 the mass times the velocity squared. We know the velocity, it's part of an orbital calculation. We know an estimate of the mass. If it's a stony or iron class object, you know the density, and if you know the size, you know the mass. So that's an easy thing to calculate, 1/2 mv squared. And it looks, the things that we have to worry about are in the red zone in both of these diagrams. Objects that are about 1 kilometer or larger, total to be something like 1 to 2,000 out there. So that's the number of objects we have to worry about for global effects. And then on this particular diagram, objects that large and larger tend to hit the Earth about every 50,000 years. A 1 kilometer size object hits the Earth about once every 50,000 years with global effects. The smaller ones hit much more frequently, have regional to local effects, and you may or may not already know this, I'll bet you don't. For 25 to 30 years, the military has kept track, because we're looking for nuclear weapons tests that aren't supposed to be conducted. And it's a fact that a yield, an impact from space, occurs about once a year, with a yield approximately the same as the atomic weapons hit on Hiroshima and Nagasaki. A few tens of kilotons explosive yield, enough to wipe out a city. Once a year. Fact. Why haven't you ever heard of that before? Well, one reason would be, not that it's a secret, you don't keep secrets like that, it's that the Earth is 2/3 water, so at the very start, 2 out of 3 impacts are going to be in the open water when nobody but the military that's watching will know. And then on land, where do people live? In tiny little targets called cities, with lots of open space in between. Last year in Peru was a major impact, not an Earth calamity one, but one that created a big hubbub for a few weeks. As one of the most recent ones. It was probably about the size of a Volkswagen Beetle. It created a crater about the size of this room. So once a year, a city killer occurs. If one of those impacts occurred smack dab on Lincoln, there would be no Lincoln, Nebraska. So that's once a year. Next picture. Don't be afraid. You're a little target. You know, cities are little targets. The important thing about the 1 kilometer size and larger is that that's enough energy to put enough dust and debris into the atmosphere and to burn such a widespread area that the soot generated from the combustion would blacken the sky worldwide and essentially bring photosynthesis to a halt for the better part of several years. That's a nuclear winter scenario that Carl Sagan and others computed could be the outcome of a nuclear exchange between the superpowers. Well, Mother Nature can do the same thing without nuclear weapons if the object is a kilometer size or larger, campus size or larger. And there's 1,000 of them out there, as I just said. And so, how many people would be killed? Well, that's a question for scientific inquiry and experiment. If you're interested in such things, this book by John Lewis is probably the single most useful book on the subject for someone who just wants to get into it. It even comes with the program that allows you to conduct your own scenarios and calculate on the basis of whether it's a stony or an iron or a cometary icy object of a certain velocity, a certain size, certain place that it's going to hit. If you work out the numbers using the physics involved, it turns out that anything a kilometer or larger will have worldwide consequences no matter what it's made out of, and occurs about once every 50,000 years. And Obviously, given the spacing of people on the Earth's surface and tsunamis and the fires that would happen in the typical cities, you can estimate the casualties. And it turns out that at the lower limit of 1 kilometer, at least 1 million people would be killed outright by the impact. And it could be 1 billion, depending on where the hit occurs. You can imagine hitting a populated coastal city, lots of people right there, and then the tsunami wave kills a lot of other people elsewhere in the world, plus the nuclear winter scenario that comes after the fact. So it's a big deal. It's fortunately a very rare occurrence, or we probably wouldn't be here to talk about it. But then the dinosaurs aren't here to talk about it either. So let's go to the next slide. Are we the dinosaurs waiting for the next rock to fall from the sky? Well, the discovery efforts are bearing fruit. As you can see, the number of projects, the 6 that are listed up here, have mounted in their discoveries and seem to be plateauing in the discoveries of the 1 kilometer size planet killer variety. And that's why we're coming down with pretty accurate numbers of about 1,000 that are out there to be worried about. Next picture. And in the case of the smaller objects, we're starting to see a drop off. So we're pretty sure we've got most of them. We're pretty sure that we've got most of the major ones discovered. We're now working on objects that are about 1/10 the size of a kilometer, 100 meters. Not even the size of this, well, maybe the size of this room from front to back. It's not quite 100 meters. Those objects will have state or regional size impacts. One example is the meteor crater in Arizona. That obliterated an area at least the size of 4 states when it occurred. Now that wouldn't be a nice scenario to happen today either, would it? So we're now in the process of finding objects that are 1/10 the size of planetary planetary threats. Next picture. Those occur very frequently, about once 1,000 years. Here's a good example. In 1972, in the Grand Tetons, a number of vacationers took still photographs like this one of a near miss. Right there it is, passing through the clouds. And if you click on it, you'll get the video that one of the other vacationers shot. You have to click it again to make it run. That object would have, based upon the brightness and the duration that it took to pass, been on the order of 10 meters across, about the width of this room, would have yielded something like the yield of the Hiroshima and Nagasaki impact. It's like the once-a-year thing. This one actually is bigger. It's by a factor of 5 bigger than the once per year. Turns out to be once per century for something like this, based upon the numbers. It happens. That was a near miss. Came within a few thousand feet of hitting the Earth. It just skimmed the atmosphere and went back out. Next picture.